Good morning, all. Myself Mahmood Batra, Assistant Professor, Dr. Disra Engineering College. This semester, I am going to take the subject network theory. The code is PCE301. In this subject, there are 8 modules: Introduction, Network Theorems, Laplace Transform, Coupled Circuits, Two-Port Network Analysis, Graph Theory and Network Equation, Filter Circuits, Fourier Method, and Waveform Analysis. These are the books. So first we'll start with the content. The content is first we have to start with the recapitulation of some part. Then nodal analysis, mesh analysis, Thevenin's theorem, Norton's theorem, superposition, maximum power transfer, Millman's and Telegrams theorem. Those theorems we will cover in this chapter. So we have started our second module. We are starting. So the basic things you already know that what is current. Electrical current is measured of the amount of electric charge transferred per unit of time. It is represented by I equals to Q by T. Unit is ampere or coulomb per second. Potential difference is the work done in moving a unit of positive charge from one point to another. It is denoted by V equals to W by K and unit is joule per coulomb or volts. Ohm's law states that the electrical current flowing in a metallic conductor is directly proportional to the potential difference at the terminal, provided the physical condition of the conductor, such as the length, the cross-section area of the conductor, temperature, material remains constant. And this is denoted by V is proportional to I or V equals to IR. R is the resistance which is constant for given conductor. Electrical resistance is the opposition that a substance offer to the flow of electric current, and it is the unit is ohm. It is denoted by R and unit is ohm. Now we are starting with the recapitulation part for chapter which is required. The basic laws of electrical engineering, that is the Kirchhoff current law and Kirchhoff voltage law. We will start with KCL. So the KCL states that the algebraic sum of currents meeting at any point in a network is zero. That is, incoming current is equals to outgoing current at any point in the network. So we are considering a part of the network, and this is the junction or node of the network, this black circle. Two currents are incoming to this node, that is I1 and I5, and three currents are outgoing, I2, I3, I4. So according to KCL law, the incoming current, that is I1 plus I5, is equals to the outgoing current, that is I2 plus I3 plus I4. Coming to Kirchhoff's voltage law, that is KVL law. It states that the algebraic sum of voltage drops across the circuit elements of any closed path is equals to the algebraic sum of the EMF in the path. So I have considered one circuit, and at current is given in the clockwise direction. Now you can see the potential E is coming here before this R1 point. Here the potential E is coming, and there is a drop across R1. After that, the potential will be decreased. So at this point, the potential will be less than E, isn't it? So that's why, as the potential is dropping across a resistance, the initial to that resistance, the potential is more, and after that it's less. That's why denoted as plus minus. Similarly, here also, in case of R2 and R3, we have denoted as plus minus. So at the end of R3, here the potential will be 0. The total voltage will be distributed among the R1, R2, R3. So some part is dropping here, then another part, and the rest is dropping here, and here the net voltage is 0. So applying KVL law, if we apply KVL law, so here I have taken the direction of current in clockwise direction, and I also move in this loop in clockwise direction. So we will start with the point with the resistance R1. As the voltage is dropping across the resistance R1, so the voltage drop will be minus I into R1, then again minus I into R2, then again minus I into R3, and here across this source, the source here the voltage is rising, negative to positive, so plus E equals to 0. This equation we are getting, and taking negative common, we are getting the second equation. Now, while we will apply this KVL law in our circuit analysis in future, no need to consider this first one, only you have to remember the second one. What you will do, you are applying the, you are considering the direction of current, and you will also move in the same direction. Whatever direction you are choosing for the current, in the same direction you will move in the loop. and you will consider the voltage drop across all the passive element as positive, and across the source. If the current is entering the source, if the current is entering negative of the source, then the voltage will be negative. If the current is entering positive of the source, then the voltage will be positive. So we will remember the second equation and we will apply this equation in our circuit analysis. Thank you.